Let me ask you something simple. Have you ever carried a heavy school bag and thought, why does it feel so heavy? That sensation of weight is actually gravity pulling the bag downward. But in physics, we love to measure things, and so, that pull of gravity has its own special unit. We call it the gravitational unit of force. It tells us how strongly gravity pulls on mass, like how much force you feel when holding a textbook or lifting a bucket of water. Now, apart from the usual unit of force, which is the Newton, we also use gravitational units in practical physics. These include the kilogram force and the gram force. And believe me, they help us connect what we learn in class with what we feel in our hands. It's all about making physics real and relatable. Let's start with the MKS system, that's the one using meters, kilograms, and seconds. Here, the gravitational unit of force is called the kilogram force. And what does it represent? It's simply the force that gravity exerts on 1 kilogram of mass. In simple words, if you hold a 1 kilogram weight in your hand, the downward pull you feel is 1 kilogram force. Of course, gravity pulls on that mass with a certain acceleration, and that's what creates the force we are talking about. The beauty of the kilogram force is that it connects the concept of force directly to mass, making it easy to picture, feel, and calculate.
Now let's take a look at the CGS system, where we work with centimeters, grams, and seconds. This system uses the gram force as its gravitational unit. And just like its name suggests, a gram force is the force that gravity applies to 1 gram of mass. Yes, even something as light as a paperclip experiences a downward pull, and that's what gram force captures. This unit is especially useful in laboratory work and fine measurements, where we deal with smaller forces and masses. It brings accuracy without overwhelming us with large values. So whether you're studying spring extensions or chemical balances, gram force plays a vital role in your toolkit. Let's now talk about switching between these gravitational units. It's like converting currencies while traveling. In the CGS system, 1 gram force is equal to about 980 dynes, dynes being the smaller unit of force here. In the MKS system, 1 kilogram force is approximately equal to 9.8 newtons, which you can think of as the standard force unit in physics. We often round this off and say 1 kilogram force is nearly equal to 10 newtons, just to keep things simple. And here's a helpful link. 1 kilogram force is exactly equal to 1000 gram force. So if you're working in different systems, you can switch back and forth easily, whether solving problems or understanding measurements in real life. Let's make this even more practical. Have you ever wondered what 1 newton of force feels like? Here's something cool. If you place a small object, say about 100 grams, in your palm, the force you feel pulling it down is approximately 1 newton. That's gravity giving you a real-time demonstration of physics. Just imagine holding a stapler, a small apple, or a pocket diary. All of those give you a pretty close sense of what 1 newton feels like. This idea helps you connect the number on paper to something you can experience physically. And that's the magic of gravitational units. They make abstract physics concrete. Alright, let's quickly go over what we've covered today. We explored 2 practical units used to express the force of gravity: kilogram force in the MKS system and gram force in the CGS system. A kilogram force tells us how much gravitational pull acts on 1 kilogram of mass, and it's close to 10 newtons. A gram force does the same for a single gram, and it equals about 980 dynes. We also learned that 1 kilogram force is the same as 1000 gram force, a handy link when working across systems. Most importantly, we saw how this concept isn't just theoretical. It's something we feel every time we lift an object. Whether you're holding a pen, a book, or a bag of flour, you're experiencing gravitational force. So the next time you pick something up, you'll know. You're not just lifting mass, you're working against gravity, and you're literally feeling physics in action. See you next time, with more amazing ways that science reveals itself in the world around us.